Okay, so last two sections we're going to look at deal with probability. So last week we already talked about counting, which is figuring out the number of ways something can occur. We're going to have to do that today. Okay, counting is part of probability, but then there's also figuring out as a percent, what are the chances that something would occur. Okay, so this is just describing like basically probability. All right, so a lot of times you have a situation that we don't know what the outcome is going to be, and we want to find the probability that certain outcomes will occur. For example, what is the chances or what is the probability that it will rain today? Okay, you see that all the time. The meteorologists or weather forecasters try to put a percent chance that it might rain. This kind of probability, a little more complicated than what we're going to do. Probably a lot. There's all kinds of computer models that go into predicting weather, probably hundreds of variables, a little more than we're going to look at. Okay, what is the probability that I would get a job I applied for? You could look at this as kind of a simple problem. If you were, say, one of 5 people that applied for the job, you could say, well, I have a 1/5 chance of getting the job, or 20% chance. But there might be more that goes into it than that. You might have certain skills or experience that somebody else doesn't have, so that might increase your chances. But again, those factors are a little bit less clear. I think it's a little vague. You know, if you said, oh, I have 3 years of experience, how does that change your chances mathematically of getting the job? Could be hard to quantify. And another example, and this one we're actually going to do tomorrow, what's the probability that an inspected part will be defective? So I could say, for example, I'll tell you the answer. Let's say there's a 1% chance that you pick up a defective part off an assembly line. If I pick out 5 parts, what are the chances that exactly 3 are defective and 2 are not? Or 4 are defective and 1 is not? Right? So we'll look at those kind of probabilities tomorrow. This last one falls into a category where there can only be 2 outcomes. A part is either defective or non-defective. That's it. That's all that can happen. Will it rain today? Okay? That you can look at that as black and white, like it either rains or it doesn't rain. All right. Some people may say, well, I could, kind of missed out or something. We have to be very clear when we do probability. Will you get the job you applied for? There's only 2 outcomes. You either get the job or you don't. All right. So we're gonna focus more on that kind of stuff tomorrow. All right, so each one of those situations, applying for a job, will it rain, all that stuff, we can think of those as experiments. Okay, so basically an experiment is a situation we're setting up. I'm going to flip a coin. That's an experiment. Getting heads or getting tails on the coin, that would be called the outcomes. Okay, so the different results of the experiment that you're doing are called the outcomes. And if we look at all the different outcomes that could happen, there's a special name for that. Does anybody know the name for all the outcomes that can happen for an experiment? Okay, it's called the sample space. Okay, so the sample space basically is every different outcome that could happen. Some sample spaces are very small, like flipping a coin. It's only 2 outcomes, heads, tails. Some sample spaces can get pretty large. And some sample spaces may even be close to infinite. When you start getting into probability that's a little bit more vague, like I was reading an example online, and they said, something about the probability, or what would be the effect of changing oil prices? What would be the probability that would cause a 15% increase in gas prices? Well, that can be tough to answer. Okay, it depends how much you change it. Depends on how much oil is available, who's producing the oil, what countries are you getting it from. So political atmospheres between different countries. So there's lots of things that affect that question. Right? But generally, we're going to look at sample spaces that are easily definable. Okay, very, very mathematically easy to calculate. Won't be vague. Okay, like this one. We're going to roll 2 dice, okay, a red die and a green die. And I want to know all the elements in the sample space. Okay, and we don't want to risk, just kind of start listing randomly. Like I could roll a red 2 and a green 3, and a red 5 and a green 6. We want some kind of method to list all the elements. So does anybody ever thought how I could list out all the elements in the sample space, but try to keep it organized? Yeah, Matthias?
Can you do that branch thing? Like we put like one of the things in the puzzle?
Oh, make like a tree?
Yeah.
We could make a tree. It's going to get really big pretty quick though, because think about it, we'd have 1 through 6 for the first roll, okay? And then off every one of those, we would have 6 outcomes. It's not too big, but it would end up being 36 branches I would have to draw.
Yeah.
But yes, you certainly could make a tree, and I'd say 36 isn't that bad, but yeah.
You make a table where you start with the red die, like if you roll 1, you can, on the other side, you can do 1, 2, 3, 4, 5, 6 with the green.
Yeah.
And then move on.
Let's just start by setting up a template. What we're going to use. And I'm going to use this over and over. So let's group that. And we'll make copies of it. All right, so Andrew's suggestion was to say, let's start with rolling a 1 on the red die. Okay, pick a specific number. And now list out all the outcomes you could have on the green die. Okay, what would be my outcomes for the green die? 1, 2, 3, 4, 5, 6. So based on this, how many times do you think I'm going to have to replicate this chart? How many columns am I going to need?
6.
Yeah, I'm going to need 6 of these. Okay, so there's 3, and we'll just put a couple below if we need to. 4, 5, and 1 more. So how many total outcomes are we going to have?
36.
Yeah. I think I mentioned that when Matthias said we could draw a tree. And a tree would be fine. The only thing is a tree doesn't actually list the outcomes like this. It helps you see them. And I'll show you another way you can see the outcomes. But they did actually say to make a list. So this is how we have to do it. And this would probably be the most I'd ever have you do. All right, what should be my next column?
2. So
Which one 2s?
the whole left column.
Yeah, the red, so red 2s.
So would this be something that's on the test? Would this be something that would be on the test?
Yep, I might ask you to list elements in a sample space. And certainly when we get to probability, you have to know how to do this anyway. Right, and then I'm just going to write these all out. So these would be rolling a red 3, red 4, red 5, and red 6. And now each column on the right, we're just going to go 1 through 6 for the green. Now, you could have done it differently. You could have said, well, I'm going to start with the green die, have that be your first column, and have the red die be your second. It doesn't matter. Just somehow do it in an organized way. Now, I had a question. Let's see if I can just copy this. Had a question in the last class whether or not it makes a difference if I switch the order. What do you think? Is rolling a red 5 and a green 1 different than rolling a green 1 and a red 5?
No.
No. If you roll the dice and just look at them the order you tell them to me, that doesn't matter. It's still the same result, whether one lands above or below or left or right on the table. Who cares? It's still the same result. Okay, and copy it one more time. Okay, so there, see if I make it a little smaller. There are all our outcomes. And how many outcomes are there? Yep, 36.
We learned last week to do that, or you can, or order doesn't matter, and you can repeat the number, so it would be just 6 for.
Yes, if they just asked for the number of outcomes, Brad, you could figure it out just to write 36. But if they do ask you to make a list of all the outcomes of the experiment, then they do want you to make a list. They actually didn't ask me to say how many, so I just said that. That was extra. Yep, but you could at least use that to figure it out. Okay, another way, I think a better way even than a tree, if you want to visualize the outcomes, is to go like this. Start with, put your red die going vertical, put the green die horizontal, and basically just make a table. This doesn't list the outcomes, but it provides a nice way of visualizing them. Okay, when I'm done, I should have 36 boxes. And one that's kind of a little crooked. Right, so now if you wanted to say, well, how did I represent a red 6 and a green 4? Yep, right there. There's your red 6, green 4. So if we have to check things off or keep track of things, I think this is a nice way to do it. Easy way to keep track of it. Okay. Any questions on that one? All right. So now we're going to look at what's called a subset of a sample space, and that's called an event. Okay, a subset means a part of it, not the whole thing, but just a small part. Okay, and here's an event from the sample space we just did in example 1. Okay, I'm going to name this event D. Okay, you can name an event with any letter you want, but I'm going to let the event D be called rolling doubles. Okay, these are the events that would fit under that category, rolling doubles. It's a small part of my sample space. In fact, it's exactly 6. There's 6 outcomes in the event rolling doubles out of a sample space of 36. Now, knowing that, I could figure out the chances of rolling doubles. Okay, here's another event. Called it event S, and it says getting a sum of 9. Okay, there's only 4 ways that you can, or 4 outcomes in the event sum of 9. So again, knowing that there's 4 outcomes, knowing there's 36 events in the sample space, I could tell you the chances of rolling 2 dice and having them add up to 9. Okay, if we were to extend it to 3 dice, okay, I wouldn't have you list the sample space, but how many elements do you think there would be if you were to roll 3 dice?
36 times 6.
Yeah, 36 times 6. Okay, every time you add another die, you multiply the outcomes by 6. Yep. And the best way to visualize rolling 3 dice would almost be if you had a 3-dimensional cube. Then you could look at like an X, a Y, and a Z position. That would be hard to draw. I think 2 dice is pretty easy, but 3 gets hard to draw. And even worse, to list out the possibilities. Okay, you'd have 36 times 6. That's a lot. All right, so this one says we're going to do an experiment consisting of tossing a coin 3 times, and we're going to record the outcomes, H for heads, T for tails. I want to list all the outcomes in the sample space. Now, sometimes it's a good idea, if you can, to do what Brad said. Just figure out how many outcomes there are first. Anybody have a guess how many outcomes are in this sample space? 6? Okay, yep, Graham. 8? Anybody else think 6 or 8? Well, let's think of it as either a permutation or combination. Which one is this? All right, I heard both. So let's look at it this way. You're making words. Your words just have T's and H's. If you change the order of the T's and H's, do you get a different word? Yes. So HHT is a different word than TTH. Right? Because we're keeping track of our results by writing down H's and T's. So let's say I flip heads 3 times. Or I flip heads, tails, and then heads. If I flip heads, heads, and then tails, that's a different event. This event and this event are different. This means I flipped heads the first time, tails the second, heads the third. This is heads the first, heads the second, tails the third. Even though it's 2 H's and a T, they're different events. Okay? So we need a systematic way to list them. And I think we did guess, somebody had guessed it right. It is 8. Because if we count, think of it kind of like we did the license plate problems. How many choices do you have for the first letter? 2. And the second? And the third. So there are 8 outcomes. Okay, very simple way to list all the possibilities. If you know there's 8, start like this. Put down 4 H's and 4 T's. Now in the next column, I want you to alternate 2 H's, 2 T's, 2 H's, 2 T's. Okay, just like that. So H, H, T, T. H, H, T, T. Now in the third column, I want you to alternate every other letter. H, T, H, T. So H, T, H, T, H, T, H, T. That gives you a very quick way to write out all the possibilities. A lot of times you do this with like true and false. It's called a truth table. So when you only have 2 outcomes to deal with, that's a method for doing it. If you wanted me to flip a coin 4 times, then I would say, well, there's 16 possibilities. I would start out with 8 H's and 8 T's, and then I'd go 4 H's, 4 T's, 4 H's, 4 T's, and then alternate 2's, 2H, 2 T's, 2H, 2 T's, and then every other letter, H, T, H, T. If you don't want to use that method, that's fine. But it is a quick method that you don't even have to think about how to do all the possibilities. Okay, any questions on the sample space? All right, so now I want to list all the outcomes in the event E. And the event E is I get at least 2 heads. Okay, so what are the outcomes in that event? At least 2 heads. Well, Tom, can you give me one outcome?
H.
Yep. H, H, H. Yep.
H, H, T.
H, H, T. Yep.
H. T.
Yep, H, T, H. What else? T, H, H. Anything else? No? So now there are 4 outcomes that fit, that are in this event. So what does that mean the chances are of getting at least 2 heads if you flip a coin 3 times?
50%.
Yeah, you have a 50% chance of that happening. Now, what if I changed it and said, what is the probability of getting exactly 2 heads if you flip a coin 3 times? Would your chances go up or go down?
No.
They'd go down. Okay, to get exactly 2 heads, HHH doesn't count. You could only have HHT, HTH, and THH. Now, what if I changed it a little more and said, what are the chances of getting 2 heads and they have to be on the first 2 flips? Would your chances go up or down? Yeah, now they go down even more. The only way you can get 2 heads on the first 2 flips is HH and then T. And they have a 1 out of 8 chance of doing that. Right, so we just have to read the question and see how it's worded. Is it exactly 2, at least 2? Does it have to be the first 2? Or can it be any 2? Any questions on that? All right. So far we've assumed that when we're doing an experiment, no particular outcome is more likely than any other outcome. Okay, when you flip a coin, we assume heads and tails, equal chance. When we roll a die, we assume 1 through 6, equal chance. Okay, that means we're assuming all the events in the sample space are equally likely. Okay, and that's not always true. Okay, we're not going to get into too many where it's not, but you could have a weighted die where the chance of getting a 3 comes up maybe 30% of the time because of the way the die is weighted. And that would change things, and it would not apply to what I'm about to show you. Okay, but we're going to assume all outcomes are equally likely. And if they are, this is how we can find the probability of an event. So the probability of an event is calculated by finding the number of outcomes in your event divided by the number of outcomes in the sample space. So the numerator and the denominator, that's where we get into counting. Okay, that's what we learned last week. How many different ways can you do something? How many total ways can you do something? That's counting. Okay, so n parentheses e, that's the number of outcomes in your event. And n parentheses s is the number of outcomes in the sample space. How come this probability always has to be between 0 and 1? All right, percents are always, 0 means it's impossible to happen. 100% means it's guaranteed to happen. But how come looking at this fraction? Why can't this fraction be bigger than 1? Yeah, the denominator is always bigger than the numerator. Okay? The denominator is all the events in the sample space. Well, you can't have more outcomes in your event than you do in the sample space. That wouldn't make sense. And there's a couple ways when we do probability you can write your answer. You can write it as a decimal between 0 and 1. You can write it as a percent. And sometimes we'll just leave it as a fraction, like 1 out of 6 or 1 out of 7. All right, so we're going to go back to example 1, rolling 2 dice. And we're going to find the probability of the event rolling a sum of 5. I thought we did that earlier, but no, we did sum of 9. Okay, so let's go back and look at that table I made. And what we'll do is we'll just check them off. Okay, find the probability of the event rolling a sum of 5. Okay, and I'll come back to that in a second. Okay, so start with row 1, and then let's go through each row and just check them off. Okay, how about if I roll a red 1? What would I have to roll to get a 5?
Green 4.
Yep, green 4. Okay, what else?
4 and 3.
Red 4 and green
3.
for a sum of 5.
Oh, I thought it was 7.
Yeah,
Oh. Oh, 1.
but you could do red 4 and
Green 1.
green 1. What else?
Red 2 and green 3.
Red 2, green 3.
Red 3, green 2.
Red 3, green 2. That's kind of almost like a mirror image, like a similarity to it. So how many different outcomes are there for rolling a sum of 5? 4 outcomes. Okay, that's the number of outcomes in our event. Number of outcomes in the event is 5. if you didn't know this, you would have to figure it out. What's the number of outcomes in the, try to make that look like an S. What's the number of outcomes in the sample space? 36. So now, what would be my fraction to find the probability of my event? Where my event is rolling a sum of 5. Oh, Heather? What would be the
How was it?
probability?
Yeah, 4.
Oh, 4, thank you. That's right. It was 4, sum of 5. So how would I find the probability of my event? Yeah, there were 4 different outcomes that was a sum of 5. 4 outcomes, sum of 5, over 36. And we'll reduce it if we can. 436 reduces to
Right.
1/9. So we could say the probability is 1/9. Or we could say that's 11.1%, or 0.1 repeating as a decimal. Okay, they're all correct. Just depends on how they ask you to write the answer. Hey, any questions on that? All right, so yeah, that was a good catch. That should be a 4, not a 5. All right. Example 4 says, what is the probability that a 5-digit telephone number chosen at random has no repeated digits? Hey, and they give us a restriction that a telephone number cannot begin with a 0 or a 1. All right, so what do you think we should find first? Ultimately, they want the probability, but there might be something we have to find first.
Sample space.
Yeah, let's find the sample space. How many outcomes are in the sample space? All right. So what kind of telephone number are we working with? How many digits? 5 digits. So we're going to do this just like we did last week. How many choices do we have for the first digit? 8. Because it says it can't begin with a 0 or 1. Now remember, this is the sample space. So this is all the phone numbers that could possibly exist, including repeats. So how many choices for your second digit?
10.
10? And 10? 10? 10? And that's it. Okay, so this is every possible phone number you could make, repeats and no repeats. How much is that? 80,000, right? Yeah. Okay, so that's how many elements in the sample space. Questions on that?
It says no repeated digits in the example.
So that's going to be our event. So the event is going to take into account the actual question. The sample space, this would be the same sample space for any single problem I asked you about 5-digit telephone numbers. So always 80,000, with the restriction they can't begin with a 0 or 1. But this is what's going to change. So now, if you can't have repeats, how many choices do you have for the first digit? 8. And the second digit? Now you have 9 choices. Back to 8, 7, and 6. Okay, we'll multiply that out, and let's see, we get 24,192. So now we know the number of elements in our event, the number of elements in the sample space. How do I get the probability of my event?
4,192
Over 80,000. Yep. And now if they just want a decimal, that's fine. We just divide it. If they want a fraction, does everybody know on the graphing calculator how to change a decimal to a fraction? It's under math, so if we type this in, 80 20,000. There we go. Okay, it's about, well, 0.3024, which is the same as 30.24%, which, as a fraction in lowest terms, we just press math. The first choice is fraction. 189 over 625. Okay, all of those are correct. Just pay attention to what the directions ask for. What was it, 625? Okay, any questions on that one? All right, so let's take a look at the term mutually exclusive. Okay, anybody know what that means, mutually exclusive? Well, what does it mean if something is excluded? It's left out, it's not part of it, right? Well, that's kind of what this has to do with. If events are mutually exclusive, it means they have no outcomes in common. So if an event already occurs if a particular outcome occurs in one event, that outcome cannot occur in the other event to have mutually exclusive events. Okay, here's an example. If we're rolling 2 dice, and I said, I want you to consider the event rolling a sum of 5 and the event rolling doubles. If you look at all the outcomes in the first event and then look at all the outcomes in the second event, they won't have any outcomes in common. You can't roll doubles and roll a sum of 5. That doesn't happen. Okay, any questions on that? That's mutually exclusive. Another example somebody came up with in my last class was rolling an even sum and rolling an odd sum. Those are mutually exclusive events. You can't roll an even sum and an odd sum at the same time. Okay. And if 2 events are mutually exclusive, we can use this formula. And it's going to be a formula to calculate the probability of either one event or another event occurring. Anybody have a guess what the formula would be? Like, actually consider that example. The probability of rolling a sum of 5 or rolling doubles. It has to do with finding each individual probability and then doing something with them. Any guess? Well, let's think. What is the probability of rolling a 5? Did that earlier. How many different outcomes were there? 4 out of 36. And how about rolling doubles? 6 out of 36. And now, what if I wanted to know the probability of either one occurring? You would add them. Yeah. And we know there's no overlap here. Okay? Rolling doubles, rolling a sum of 5, you didn't accidentally count anything twice. Okay? That would be a problem if you did. Okay? So you take each individual probability and add them up. That's how you find the probability of one event or the other. Okay, and we're using or in the sense that it can be either A or B, and they're mutually exclusive. All right, so let's try this one. Okay, so this says that we're going to take 1 card out of a deck of 20. Right, so we're not dealing with a complete deck of cards. Okay, only 20 cards. And the 20 cards are made up of aces, kings, queens, jacks, and tens. And I have each one of those cards in their 4 suits. So I have ace of hearts, ace of spades, ace of clubs, ace of diamonds. King of hearts, king of spades, king of clubs, king of diamonds. So I have 4 aces, 4 kings, 4 queens, 4 jacks, 4 tens. That's my 20 cards. Okay, I want to know the probability of drawing a 10 or a face card. Okay, and if you're not sure again what a face card is, just a reminder, a face card is a king, queen, or jack.
75%. Yeah. 80%.
So let's start with the probability of, what's the probability of getting a 10?
4%. 20%.
Yep, so 4 out of how many? 20. There's a 10 of spades, 10 of hearts, 10 of clubs, 10 of diamonds. So 4 tens. And how many face cards are in this deck of 20? 12 face cards. Okay, so we have a 16 out of 20 chance, or if you reduce that as a fraction, it would be,
4.
you have a 4/5 chance of having this event occur. And I heard some of you say that's 80%, or 0.8. So that's pretty likely. It's pretty likely that'll happen. Any questions on that one? All right. Now, what would be the opposite of this event occurring? How could you word that? What if I wanted to know exactly the opposite of this occurring? And I'll give you a hint. There's a 4 out of 20 chance that what I'm trying to get you to say would happen. Yep.
You draw an ace.
You draw an ace. Right? When we talk about what's called the opposite of something occurring, that's called the complement. So the complement of an event, we write with this, let me make it a little bigger, this symbol A with a C where an exponent would be. And the complement of an event is everything that's in the sample space that's not in your event. Okay, so if your event is drawing a 10, king, queen, or jack, the complement is everything that's not what I just said, drawing an ace. Okay, and this next question, I just want you to think about it for a second. If you compare the number of elements or the number of outcomes in an event or its complement to the number of outcomes in the sample space, how would those two compare to each other? Think about the number of elements in an event or the complement of that event, and then find the number of elements in the sample space and compare the two numbers. What would you notice? Brad?
The number of elements in the sample space would be, well, you would subtract the complement from the sample space and get the event, or you would subtract the event from the sample space and get the complement.
All right, so I see what you're saying. You're actually jumping ahead a little bit to something we're gonna mention. But if you just look without doing any kind of subtraction, just think of the number of elements in an event, find that, find the number of elements in the complement of that event and add them up. And then take the number of elements in the sample space.
They're going to be the same.
Yeah, they're going to be exactly the same. So this covers every possible event you could have. Okay? It's either, in my sample, it's either a particular outcome is either part of the event or it's not part of the event. It's one or the other. Okay? So this covers everything that could possibly happen. Okay, so from the previous page, this is our formula. The probability of an event or its complement is the probability of the event plus the probability of its complement. Same formula I just used right here. What's the probability of something, of an event, of an outcome in an event, or an outcome in the complement of that event?
100%.
It's a 100% chance that you're going to get an outcome that's either in your event or it's not in your event. Okay, it's a 100% chance, which we can write as 1. And now, let's say I wanted a formula to get this by itself. How would I move probability of A to the other side?
Subtract it.
Subtract it. And that's, I think, what Brad was starting to mention. If you want to find the probability of the complement of an event, it's 1 minus the probability of your event. And you might say, well, why would we bother with finding the probability of a complement of an event? Well, that's actually sometimes a lot easier to do. Okay, so you're going to see this in the next problem. But sometimes it's easier to actually find the probability of the complement of your event rather than finding the probability of the event itself. Because if you can find the probability of the complement, you can just use this formula and find the probability of the event. In our next example, we'll show you why you might want to do that. So example 6 says you're going to be dealt a 13-card hand out of the entire deck, 52 cards. I want to find the probability that the hand you are dealt has at least 1 heart. What does that mean when they write the phrase at least 1 heart? All right, so give me a specific number. You said it could have more than 1.
7.
Could have 7 hearts. What else? Yeah?
Could have 13.
13 hearts. We would have to find every probability. We would have to find the probability, okay, and we're not going to do it this way, of exactly 1 heart plus the probability of exactly 2 hearts plus the probability of exactly 3 hearts, 4 hearts, 5 hearts, 6, 7, 8, 9, 10, 11, 12, and 13. Okay? Because that's what the phrase at least means. So we'd have to find all those probabilities. So we'd have to go through and find like 13 different probabilities. Okay? Not efficient. Let's look at doing it as the complement. Okay? What's the complement of my event? Yeah, it's that I have no hearts. So let's find getting exactly no hearts, and then all we have to do is solve using our formula right there. All right, so we'll just define our event as getting at least 1 heart. At least 1 heart in a 13-card hand. So the probability, actually, you know what, that's not, oh, bless you. That's not really the probability of my event, that's just the event. So I'm going to write it that way. Okay, and the complement of my event, we are dealt 0 hearts. In a 13-card hand. Any questions about what the event is here or what its complement is? All right, so let's try to find the complement of our event. What's the first thing I should probably find? And I have to do this pretty much in any probability problem. Yeah?
The sample space.
Yeah, we got to figure out the sample space. How many different outcomes are there? Okay. Is this problem a combination or permutation? Why is it a combination?
Because it doesn't really matter what the order is, it's just how many cards you get, because it's a path.
Or what cards you get? Yeah, it doesn't matter the order you get the cards in, okay, or the order you hold them in your hand. As long as you have the cards, order doesn't matter. So that's a combination. So how would I figure out my sample space? It's a combination of how many cards are we choosing and how many are in the sample space.
Wait, say that again?
So I want to first figure out my sample space. So it's a combination of what choose what.
52,
Out of the 52, you're going to choose
13.
13. Okay. And we can figure that out. Does anybody remember the formula for a combination?
N factorial
N factorial,
over n minus r factorial,
n minus r factorial,
r factorial.
r factorial. Now, we could go through and do that out. Okay, that's what we did on the last test. Or we can use our calculator, and that is already built in for us. Okay, so if we just go to math, go to probability, and the third option down is for combinations. And you can just type it in. So we've got 52, choose 13. All right, so that's a pretty big number, 6.35 times 10 to the 11th. What I'm actually going to do is I'm going to save that answer in the memory for now. I'm just going to store that answer as A. So now I can clear the screen, and anytime I want that answer back, I just press A, and it'll come right back. Okay, so I saved that in A. Okay, I'm actually going to write that here. Save in A, so I don't forget. Now I've got the number of elements in my sample space. Now I need the number of elements in my event. Oh, I'm sorry, the complement of my event. Now we're going to focus on this. If I want to get 0 hearts, how many cards are left in the deck that I can actually work with?
39.
Yeah, there's 13 different cards. Each card is in 4 suits. So there's 13 hearts, 13 clubs, 13 spades, 13 diamonds. So you take 52, take away all the hearts in the deck, you're left with 39. And out of those 39, how many are we choosing for a hand? 13. Okay. So this is, let me write down what we're finding. It's the number of outcomes in our event. Okay, can I use capital E? I use capital E. All right, I'm going to do the same thing. I'm just going to use the calculator again. So I've got, all right, 39, choose 13, and you get, let's see, 8122,425. Is that right? Yeah. And I'm just going to store that answer as B, just so I don't have to type it in again. Okay, and I'll write stored in B. Now I've calculated number of outcomes in my event, number of outcomes in my sample space. So how do I find the probability of my event? what's going to go on the top part of that fraction? About the top? What is it?
The one that we just wrote.
Yeah, B. Okay, the number of outcomes in my event. Oh, I'm sorry, thank you. Complement of my event. So that's, I'm just going to write B because that's what we stored it as in the calculator. Divided by the number of outcomes in my sample space. And what did we save that as? A. Okay. So just divide those two on the calculator and see what we got. B divided by A. 0.0128 if we round it off. Okay, again, that's the probability of the complement of my event. So is that the answer they're looking for? No, that's the chances of the opposite of what I want. So what do I basically have to do to figure out the chances of what I do want? Yeah, it's just going to end up being 1 minus that. We just subtract it. 1 minus 0.0128, and this is the probability of my event, not its complement. Okay, so we have a pretty good chance of our event occurring. Okay, 0.9872. Okay, which is about 98, or exactly 98.72. So the chances of you getting at least one heart are pretty likely. 98.7% chance. Hey, any questions on that? Okay, now if we were doing this the other way, we would only be done the first calculation at this point. We would know the probability of, say, exactly one heart. Then we'd have to do it for 2, 3, 4, 5, 6. Okay, it would take a lot longer. All right, so hopefully you can see the advantage of working with the complement. All right, and the last thing we're going to look at is what's called independent events. And we'll look at that in 1 second. All right, so what does it mean if things are independent of each other? Yeah, they don't need each other, they don't depend on each other, and that's pretty much the same thing with probability. Okay? If two events are independent, it means that one has no effect on the other. For example, tossing a coin. I don't care if you toss a coin and you get heads 10 times in a row, the chances of getting heads again is still 50-50. It's 50-50 every time. It's not likely that you would get heads 10 times in a row, but that doesn't affect what's going to come up on the 11th flip. Still 50-50 chance, theoretically. Question? Yeah. Okay. And for events that are independent, have no effect on each other, we can use the following formula. The probability of event A and event B occurring, not or, this is and, is the probability of event A times the probability of event B. So if you had a spinner, say had numbers 1 through 10, and you had a coin, I could say, what are the chances of you spinning a 5 and flipping heads on a coin? Both happening at the same time. And those are independent. Flipping a coin, spinning a spinner, has no effect on each other. All right, so here's the event here is flipping a coin. And how many times are we going to repeat, or this experiment, I should say, how many times are we going to repeat the experiment of flipping a coin?
3 times.
Yeah, we're going to do it 3 times. And we want to know what are the chances of getting exactly heads, tails, heads.
1 in 8.
Yeah. So this one's pretty simple. You can really figure it out. But if you're stuck, the way I think of it, find the probability of what you want on the first flip times the probability of what you want on the second flip times the probability of what you want on the third flip. Okay, what do you want to happen on flip 1? Heads. How many ways can you get heads when you flip a coin? 1 out of how many?
2.
1 out of 2 outcomes. What do you want to happen on the second flip?
Tails.
Tails? 1 tail out of 2. Third flip?
Heads, 1 out of 2.
And there's 1 heads out of 2 possibilities. Multiply together, 1/8. Okay. Any questions on that? Any questions on how to change that to a percent if I ask you to? Using calculator? All right. All right, so up until now, everything we've done, we assumed what's called theoretical probability, which means it's purely mathematical. Okay, you didn't actually go out and do the experiment. It's just based on mathematics. Well, another kind of probability is called experimental probability. That's where you actually go out and try to do what it is you're asking. Now, if you were going to ask me to flip a coin 100 times and record the number of heads and tails, I probably wouldn't actually do the experiment. What I could do is use the random number generator on the calculator, have it generate numbers that are either zeros or ones, and we'll call 0 heads and we'll call 1 tails. And I could just let the calculator generate random numbers 100 times. Right? And it gives me kind of a quick way of doing it. Or I could generate the numbers 0 through 9. And I could say if you get 0, 1, 2, 3, 4, it's heads. Or if you get 5, 6, 7, 8, 9, it's tails. So you have an equal chance of heads and tails. And let the calculator do it. How would you do it? Under math, you've got to use the random number generator. And what this will do is if I do it like this, it just generates random numbers between 0 and 1. So what I'm going to do is say multiply those by 10. And because I don't really care about the decimal, I'm just going to take the integer part. So I could go number, integer part. And now, basically, I'm generating random numbers. So I could say, again, 0 through whatever is heads, whatever through the end is tails. We just have to make sure that it's 50-50. Okay? So in this case, I'd say 9 is a tails, 1 is a head, 5 is tails, 4 is heads, 7 is tails. Gives me a quick way to simulate the experiment. So in this case, if you flip a coin 100 times, you get heads 48. What's the experimental probability of heads? Yeah, 48 out of 100, or 40.48, 48%. Now, if you all did this experiment, and I looked at all your experimental probabilities, would they all be the same?
It's not like
There's a chance.
Right, they should be close to the theoretical probability. Okay? Anytime you do experiments, they should come close to theoretical. And what do you think happens the more and more flips you do of this coin?
the closer you get to
The closer it gets to the theoretical. So if you flip it 1,000 times, you're probably going to be even closer than 0.48. If you flip 1,000,000, even closer. Okay? So theoretical probability is exact. It's always the same for everybody every time. Experimental probability can be different, okay, because it's an actual experiment. Okay, so I want you to tell me the answer to this, but make sure you just read it carefully. Toss a coin 55 times, heads occurs 26. What's the experimental probability of getting tails? It's not a hard question, it's just a little worded a little differently than the last one. So I'm going to be careful. Anyone think they got it? Brad?
The 29,
Okay, how'd you get 29? Where'd that come from?
55 minus 26.
Right. It's not asking you the experimental probability of getting heads, which would be 26 out of 55. It says tails, which is 29 out of 55. Okay, any questions on that? All right, so that's kind of a basic intro to probability. Tomorrow we'll continue looking at it, and then we'll have a discussion about what we'll do for our test later on. Okay, so the homework in your book on 665, 2 to 30, just evens. Okay, 2 to 30, just the evens.